So previously, we assumed that even if we were talking about repeated games, that the players are making their decisions simultaneously. They're happening at the same time. Now we're going to relax that assumption because a lot of times players make decisions one at a time, not at the same time. These types of games are called sequential games. That is, one player moves first, and the other player observes this action before making their own decision. The matrix approach that we have been using to solve for games for simultaneous move games will not work for sequential games. So instead, we're going to use what we call extensive form games or decision trees. These decision trees represent sequential games, and they show both the player's choice and the timing of the player's actions. So let's go back to the case of Warner Brothers and Disney deciding when to release the Lego Movie 2 and Frozen 2. There are three possible release months: March, May, and December. Previously, we had this extensive form or normal form game, and we saw that there were two possible Nash equilibria, one in May, December, and the other in December, May. Uh, this is still the normal form. This is still the two firms deciding when to release their movies at the same time without observing what the other one's doing. Uh, Now we're going to relax that assumption and assume that Warner Brothers moves first, committing to a release date that Disney can observe. We're going to use backwards induction to evaluate the Nash equilibrium. For each strategy that Warner Brothers might choose, evaluate the best response by Disney. These outcomes are what we call subgame equilibria. This will become more clear when you see the game tree. So Warner Brothers chooses a strategy that results in the most favorable outcome given knowledge of Disney's best response. So even though Warner Brothers moves first, they also know, based on how they move, what Disney will choose to do. So in setting up the game tree, Warner Brothers moves first. Warner Brothers can choose between May, December, and March. Disney can choose responds to each of those options by choosing May, December, or March, May, December, or March, May, December, or March. So in order to solve this game, you have to work backwards. Imagine then that Warner Brothers first is evaluating whether or not they should release in March. If they release in March, they can figure out that Disney will be choosing between these three options. So Disney's payoffs are 300, 200, and negative 50, and so Disney will choose this 300. Knowing that Disney will choose that 300 and release in May, Warner Brothers knows that if they choose March, they'll get a payoff of 100. Do the same thing for the middle column when Warner Brothers releases in December. Look at Disney's options: 300, 0, and 100. Again, Disney chooses to release in May. Warner Brothers knows that if it releases in December, Disney will release in May. Warner Brothers' payoff is 200, and Disney's payoff is 300. Do the same thing for Warner Brothers releasing in May. You look at what Disney is choosing to do. They're choosing between 50, 200, and 100. So Disney chooses 200. So Warner Brothers knows if they release in May, Disney will choose December, and Warner Brothers will get a payoff of 300. So by knowing Disney's best response to each release date, Warner Brothers will choose May, and that will be the Nash equilibrium. Why? Because Warner Brothers knows that Disney will choose December here, May here, and May here, and so Warner Brothers is evaluating between 100, 200, and 300. Since they move first, they have this first mover advantage. They'll choose to release in May, forcing Disney to release in December, and Warner Brothers ends up with the 300 payoff. There's another type of sequential game called player pass that has a slightly different structure than the one we just saw. So imagine that you have two guys, Dan and Patrick, and they're playing this game called player pass. They flip a coin to decide who moves first. Dan wins. Dan then can choose to play, which ends the game with a payoff of 1 for him and -10 for Patrick, or to pass, which moves the game to Patrick. If Patrick chooses to play, he receives 12 and Dan receives 0. If he chooses to pass, each player receives 11. So what does this look like in a game tree? You have Dan moving first. If he passes, then Patrick gets to decide whether to pass or play. But if Dan plays, then Patrick doesn't get to make a choice. Go through the same situation as before. Imagine we're solving backwards, so imagine that you're Patrick and you're choosing between 11 and 12 if Dan passes, so you're going to choose 12. Now you're Dan, and you're Dan trying to make his decision. He knows that if he passes, Patrick will pick play, and Dan will get a payoff of 0. So he's comparing this payoff of 0 to playing and getting this payoff of 1. So Dan will always choose to play. Patrick never gets to make his choice. Dan ends up with a payoff of 1, and Patrick ends up with a payoff of -10.